This is lecture 5 of 11. We're going to continue talking about second order and higher order linear equations. We'll talk about repeated roots of the characteristic equation. We'll talk about the method of reduction of order. And then we'll start talking about non-homogeneous equations. The first part of non-homogeneous equations we'll do this week, the method of undetermined coefficients. And we'll continue talking about non-homogeneous equations next week. A quick recap of yesterday's lesson, first of all. If I wanted to solve the homogeneous equation, ay double prime plus by prime plus cy is equal to 0, which has constant coefficients, a, b, and c, then we need to find two linearly independent solutions, y1 and y2. As soon as we know these two linearly independent solutions, we can write down that the general solution is c1y1 plus c2y2 for constant c1 and c2. The way that we solve this equation is first we write down the characteristic equation. That's the same numbers, a, b, and c, but now in a quadratic equation, ar squared plus br plus c is equal to 0. And we need to find the roots of this characteristic equation. Then there's three possibilities for the roots. If we have two different real numbers, then the two functions that we want are e to the power r1t and e to the power r2t. If we have complex conjugates, then the two functions that we want are e to the lambda t cos mu t and e to the lambda t sine mu t. That's what we did yesterday. We didn't talk about what happens if the roots are repeated. So let's do that now. What do we do if we have repeated roots to the characteristic equation? We're looking at the differential equation ay double prime plus by prime plus cy is equal to 0. But now we're going to be supposing that b squared minus 4ac is equal to 0. Then that means that in our formula for the solution of a quadratic equation, we just have a square root of 0. In other words, we have the repeated root minus b over 2a. So we know one solution. We know e to the power r1t, or in this case, e to the power minus bt over 2a is a solution. But to be able to write down the general solution of a second order equation, we need two linearly independent solutions. So the question becomes, how do we find a second solution? Let's look at an example. Solve y double prime plus 4y prime plus 4y is equal to 0. The characteristic equation, r squared plus 4r plus 4 equal to 0, we can factor this as r plus 2 squared is equal to 0. So we have repeated root minus 2. We know one solution. We know that e to the power minus 2t is a solution of the differential equation. We need to find a second linearly independent solution. And the idea is this. We know that y1 is a solution. We know that if we can multiply y1 by any constant, we still have a solution. Maybe instead of multiplying by a constant, we can multiply by some special function vt. And if we've chosen the correct vt, maybe we still have a solution. So we're going to be thinking about y2 equal to vt multiplied by y1t for some special function vt, which we don't know yet. We need two derivatives of this. We can calculate this using the product rule. y2 prime must be v prime e to the power minus 2t minus 2v e to the minus 2t. And then differentiate again using the product rule. V double prime e to the minus 2t. Differentiate the e to the minus 2t, we get a minus 2 in the front. That's the same as what we would get from differentiating the v in the second term, so we end up with minus 4. And then in the second term, differentiate e to the power minus 2t, we get another factor of minus 2, that becomes plus 4v e to the power minus 2t. And then we're going to put these into the differential equation. I want to have y2 double prime plus 4y2 prime plus 4y2 is equal to 0, because I want y2 to satisfy this differential equation. Substituting in the red, green, and orange formulae and rearranging and cancelling, this simplifies to v double prime e to the power minus 2t. We'll put this at the top. We want v to satisfy this equation. Because an exponential function is always non-zero, this tells us that we must have v double prime is equal to 0. We could choose any function v which has its second derivative equal to 0. And I like easy functions, I like simple functions, so I'm just going to choose the easiest one that I can think of. I'm going to choose vt is equal to t. So therefore, we have y2 is v multiplied by y1, y2 must be t multiplied by e to the power minus 2t. But wait a minute, we have two solutions. Are these two solutions linearly independent? To answer this, we calculate the Wronskian. The Wronskian of y1 and y2 is always non-zero. So the answer is yes. We have two different solutions which are linearly independent. Therefore, we have a fundamental set of solutions, and we can write down that the general solution is c1 e to the power minus 2t plus c2 t e to the power minus 2t. We can use the same method for the general equation ay double prime plus by prime plus cy is equal to 0. We know one solution, we know e to the power minus bt over 2a, and then we're going to guess that the second solution is some function vt multiplied by y1. I'm going to differentiate this 2 times and then put into the differential equation. And I'm going to leave this for you to do. You fill in the gaps here. I'm not going to go through all of the details. You can check that if we substitute this y2 into the differential equation, we end up with 0 is equal to a e to the power minus bt over 2a v double prime. Now, because we have a second order equation, a is not equal to 0. An exponential function is always not equal to 0. So we must have that v double prime is equal to 0 again. So just as before, we could choose vt equal to t, and our second solution is then t multiplied by y1, or in this case, t multiplied by e to the power minus bt over 2a. To be sure that these two solutions are linearly independent, we would need to calculate the Wronskian, but I'm going to leave this for you to do. Please calculate the Wronskian of e to the power rt and t e to the power rt, and check that this is non-zero. Therefore, we have a fundamental set of solutions to equation 1, and then we can write down the general solution. For example, solve y double prime minus y prime plus 1/4 y is equal to 0 with the initial conditions y of 0 is 2, y prime of 0 is 1/3. We start with the characteristic equation, and we see that we have repeated root 1/2. As soon as we know the roots, we can write down the general solution to the differential equation. Because if we have repeated roots, it's always constant e to the power rt plus constant t e to the power rt. So in this case, c1 e to the power t over 2 plus c2 t e to the power t over 2. And that's all we need to do to find the general solution of this differential equation. To finish this problem, to find the solution to the initial value problem, we need to find c1 and c2. Because the derivative of y is this function, when we replace t by 0, we end up with 2 is equal to c1 plus 0, and 1/3 is equal to a half c1 plus c2 plus 0. So c1 must be 2, and c2 must be minus 2/3. And that's it, then we're finished. Then we can write down that the solution to the initial value problem, y is equal to 2 e to the power t over 2, minus 2/3 t e to the power t over 2. I'll show you a graph of this function later. First, another example. Solve y double prime minus y prime plus 1/4 y is equal to 0 with the initial conditions y of 0 is equal to 2, y prime of 0 is equal to 2. This is almost the same as the previous example, but now I've changed the second initial condition. And I'm not going to answer this, I'm going to leave this for you to do. Solve this problem, and please check that the solution to this example is 2 e to the power t over 2 plus t e to the power t over 2. I'm going to show you the graph of this function and the graph of the solution to the previous example. The solutions to two initial value problems here. Both initial value problems have the same differential equation, and they both have the same first initial condition, y0 is equal to 2, which tells us that when t is equal to 0, y is equal to 0. In other words, we pass through the point 0, 2. And the second initial conditions are not that different. It's not like one is plus 1,000,000 and the other one is minus 1,000,000. We have y prime 0 is equal to 2 and y prime 0 is equal to 1/3. They're quite similar. They're not that different. And yet the behavior of the solutions is very different. The red curve goes down to minus infinity as t increases. This blue curve, or this teal curve, goes up to plus infinity when t increases. Now we can fill in the summary. To solve a second order linear ordinary differential equation, homogeneous with constant coefficients, we need to find two linearly independent solutions. Case 1 and case 2 we did yesterday. We've just done case 3. If we have repeated roots, then the two functions that we want are e to the power rt and t e to the power rt. That brings us neatly into the method of reduction of order. In this section, we're going to be looking at equations of the form y double prime plus pt y prime plus qty is equal to 0 for some functions p and q. Now let's suppose we know one solution to this differential equation, and suppose that we want to find a second linearly independent solution, so that we would have a fundamental set of solutions and then we could write down the general solution. What do? The main idea in this section is that we're going to be making a guess. We're going to guess that y2 is equal to some function vt multiplied by y1. If we can find vt, then we have our second solution, y2. So a similar idea to the idea from the previous section, but generalized. So we're going to start by guessing that y2 is v multiplied by 1. We're going to differentiate this 2 times, and then we're going to substitute these formulae into the differential equation. We're starting with the equation that we want to be true. We want to have y2 double prime plus py2 prime plus qy2 is equal to 0, where p and q are functions. And we want to find an equation for v. So what we do is we substitute these orange, green, and red formula in, and then we rearrange. We have v double prime y1 plus v prime 2y1 prime plus py1 plus v y1 double prime plus py1 prime plus qy1. And I'll leave this for you to check. Now, remember, we're starting with y1 being a solution to the differential equation. So we're starting by knowing that this final bracket must be equal to 0. So we just have v double prime y1 plus v prime multiplied by 2 y1 prime plus py1. Let me make some remarks. The key thing to note here is that because y1 is a solution of the differential equation, we must always have 0v when we do this. It's okay to have v double prime terms, and it's okay to have v prime terms, but we shouldn't have any v terms. We should always get 0v. If you do a reduction of order question and you don't get a 0 here, if you get something else, then you know that you've made a mistake in your calculation. You'll need to go back to the start and find your mistake. I also want to remark that this is actually not a second order differential equation. This is actually a first order differential equation for v prime. Instinctively, we think this is a second order equation because there's 2 derivatives here. But if we make the substitution u is equal to v prime, you can see that we actually only have one derivative on top of a variable. Is that we actually only have a first order differential equation. So instead of having to solve a second order equation that we started with, we only have to solve a first order equation. If we can find u, which solves equation 4, then we can integrate it to find v, and then we can multiply v by y1 to find y2. So in other words, if we can find u, then we can solve the problem. We started the problem with a second order differential equation for y2, but we've changed this into a problem where we only need to solve a first order differential equation for u. This is why this method is called reduction of order. Now, Let me just summarize the method, summarize the ideas here. For reduction of order, we're going to start by guessing that y2 is v multiplied by 1, y1, for some non-constant function v. We're going to put this into the differential equation, and we're going to find an equation for v. Step 3, we're going to substitute u is equal to v prime. We can do this because there are no v terms if we haven't made mistakes. Step 4, we're going to solve a first order equation to find u. As soon as we find u, we know that we can finish. We integrate this to find v, and then we multiply by y1 to get y2. Let's do an example. And typically, reduction of order questions I would write like this. Given that 1 over t is a solution of this differential equation, find a linearly independent second solution. If you see a question written like this, then it's a reduction of order question. We're told one solution, we're told that 1 over t is a solution, and we're being asked to use the reduction of order to find a second solution. So we're starting with y1 is 1 over t, and we're going to make the guess that y2 is v multiplied by y1. We'll do our derivatives first of all. y2 is v t to the power minus 1, so y2 prime must be v prime t to the power minus 1 minus v t to the power minus 2, and then differentiate again. y2 double prime must be v double prime t to the power minus 1 minus 2 times v prime t to the power minus 2 plus 2v t to the power minus 3. For the middle term, I'm combining two derivatives. If we differentiate the t to the power minus 1, we're going to get minus v prime t to the power minus 2. In the second term, if we differentiate the v, we get v prime. Add these together, 1 plus 1 is 2. And then we're going to take these functions and we're going to substitute them into the differential equation that we want to be true. Here we go. And then we're going to rearrange. First, I'm going to group all of the v double prime terms, and then I'm going to group up the v prime terms, and then I'm going to group up the v terms, like this. Now, remember, we must always have 0 v. Whatever we have in this last bracket should be 0. Let's quickly check this, check that we haven't made a mistake. 4 minus 3 minus 1 is 0. Yes, that's what we should have. This simplifies to 2t v double prime minus v prime. We have our differential equation for v. We do a substitution. We're going to let u be equal to v prime. And the first order equation that we want to solve will be 2t du dt minus u is equal to 0. This equation is both linear and separable. So we know 2 ways to solve this equation. I'm going to solve this as a separable equation. I'm going to be very quick here. This should be revision for you. You can come back and check this later. First, I rearrange so that all of the u terms are on the left and all the t terms on the right. If I can do this, then I'm allowed to integrate. Integrate, rearrange, etc. We end up with u is equal to some constant c multiplied by t to the power of a half. I've been deliberately very quick here. I'm going to move ahead. So we found u now. To get v, we integrate. V is the integral of u. That's 2/3 c t to the power 3/2 plus a new constant, which now I'm calling k. So then y2 is going to be v multiplied by y1. y1 was just 1 divided by t, so y2 must be 2/3 c t to the power of a half plus k t to the power minus 1. I'm not quite finished. I want to simplify this a little bit. Remember that we're trying to find a solution which is linearly independent from y1. The second term of y2, as we have it written, is just a constant multiplied by y1. And we don't need this. We're trying to find something that's linearly independent. We don't want just a constant multiplied by y1. So we're going to just forget this. We don't need this. We don't want it. So we could just choose k is equal to 0. Forget about this term. So far we have y2 is 2/3 c t to the power of a half. And this will be our solution for any non-zero c. But I like easy functions. I like simple functions. I don't want anything complicated. I'm going to choose c to be equal to 3/2, just to simplify this to y2 is equal to t to the power of a half. And that's going to be the answer to this question. I'm going to leave it for you to check that the Wronskian of these two functions is not always 0. In other words, I'm leaving it for you to check that these two solutions are linearly independent. Let's do another one. Given that the function t solves this differential equation, find a second linearly independent solution. We know our method. We're going to guess that y2 is some function v multiplied by y1, and we're going to find that function. So we start with y2 is equal to v multiplied by y1, or v multiplied by t. Differentiate 2 times, and then substitute into the equation. Again, I'm being quick here. You can come back at a later time and check there's no mistakes here. I think that we get 0 is equal to t squared t v double prime plus 4v prime. And just let me say again, we must always get 0v here. We don't want any v terms. The question said that t was always a positive number, so we can forget about the t squared at the start. We do our substitution, let u be equal to v prime, and we get a first order differential equation, t du dt plus 4u. This is the equation that we want to solve. Again, this equation is linear, and this equation is separable. I'm solving this as a separable equation. I'll leave the details for you to check. And I get that u is some constant c multiplied by t to the power minus 4. So to recap, we started with y1 is equal to t. We did the substitution, v prime is equal to u, and we found that u is equal to c t to the power minus 4. Integrating u gives v. V must be minus 1/3 c t to the power minus 3 plus k. We don't need the k term. Always we don't need the k term. We can forget about that. We're going to choose the value of c just to simplify this. y2 must be vt multiplied by t, or minus 1/3 c t to the power minus 2. And then, just to make this look nice and simple, we can choose c is equal to minus 3, and we can get the answer to this question. y2 is t to the power minus 2. Okay. So that would be the end of the question, if you were asked it. But if we have time in the exam or time when you're doing your homework, you might want to do a couple of quick double checks just to make sure you haven't made a mistake. Does t to the power minus 2 really solve this equation? Just quickly check to see if we've made any mistakes. Differentiate 2 times, substitute in, and what do we get? We get e equal to 0. So the answer is yes. This function really does solve the differential equation. Second question, are these two functions really linearly independent? To answer this, we calculate the Wronskian, and we find that w is minus 3t to the power minus 2. Because t is always positive, we can straight away say this is non-zero. So therefore, y1 and y2 are linearly independent. Two quick checks which tell us that we haven't made a mistake in our calculation. For the rest of today's lesson, we're going to be talking about non-homogeneous equations. Now we're going to be looking at equations of the form y double prime plus pty prime plus qty is equal to gt. If we replaced the gt by 0, we get a new equation which is called the homogeneous equation corresponding to the equation that we started with. Now, how do we solve a non-homogeneous equation like this? We can write the general solution like this. We can write it as c1y1 plus c2y2 plus an extra term plus, I'm using the notation capital Y, where y1 and y2 form a fundamental set of solutions to the homogeneous equation corresponding to our differential equation. C1 and C2 are constants. So in other words, we start with the general solution to the homogeneous equation, and then we do plus something else. And the something else is a particular solution to our non-homogeneous equation. In other words, it's just one equation, one solution that we can find, any solution that we can find. So what's our method to solve a non-homogeneous equation? If we want to solve the non-homogeneous equation L of y is equal to g, using my shortened notation from yesterday, step 1, we find the general solution to the homogeneous equation corresponding to our equation. Step 2, we're going to find a particular solution to our non-homogeneous equation, and then we're going to add these two functions together. You know how to do part 1, part 3 is easy, but how do we do part 2? We're going to be doing two methods. We're going to study two methods to do the second step. One method we're going to do today, and the other method we're going to look at next week. Today we're going to look at a method called the method of undetermined coefficients. And it goes like this. The idea is we're going to look at the function g of t, and we're going to make a guess. And we're going to make a guess which includes constants. And then we're going to try to find the constants. For example, find a particular solution to y double prime minus 3y prime minus 4y is equal to 3e to the power 2t. We have gt equal to 3e to the power 2t. That's a number multiplied by e to the power 2t. And we're going to make a guess. We're going to guess that our particular solution is of the same form. We're going to guess that the particular solution is also a number multiplied by e to the power 2t. So the guess we're going to do is we're going to guess that the particular solution is some constant capital A multiplied by e to the power 2t. Let me repeat that idea. We look at gt, here that's 3e to the power 2t, and then we make a guess. And we make a guess which is of the same form. Our function is number multiplied by e to the power 2t, so our guess is also going to be number multiplied by e to the power 2t. And then we need to find the constant a. We differentiate 2 times, and then we're going to substitute into the equation. Start just here. I want to find the function capital Y, which satisfies y double prime minus 3y prime minus 4y is equal to 3e to the power 2t. So I'm starting with this, and I'm going to substitute in my guess instead of capital Y. And you can check that after we put this in and we simplify, the right-hand side becomes minus 6a e to the power 2t. And of course, these must be the same. 3 must be the same as minus 6a. So we need to have capital A as minus a half. And then we're done. Therefore, a particular solution is minus a half e to the power 2t. Look at the function gt, make a guess, which is of the same form, find all of the constants, and then we're done. Next example, find a particular solution to y double prime minus 3y prime minus 4y is equal to 4t squared minus 1. Here's the function that we look at. We look at 4t squared minus 1. What type of function is this? This is a polynomial. This is a second degree polynomial. So we're going to do this guess. Because this is a second degree polynomial, we're going to guess that capital Y is also a second degree polynomial. The guess that we make is at squared plus bt plus c, just any second degree polynomial. I'm going to leave this example for you to finish. I'm not going to do this. Just substitute in the polynomial into the differential equation and find the numbers a, b, and c. There's a new word on this page, perhaps a new word for you. This word ansatz means a mathematical guess. I'm going to start using this instead of using the word guess. For example, find a particular solution to y double prime minus 3y prime minus 4y is equal to 2 sine t. Now our function is a number multiplied by sine t. So it makes sense to try the ansatz, number multiplied by sine t. And this is going to be my first guess. There's a clue here. Why is it first guess? Straight away, you're probably thinking something is going to go wrong here. This is not going to work. Let's try this. Differentiate 2 times, put it into the differential equation, and we end up with 2 sine t is equal to minus 5a sine t minus 3a cos t. So on the left there's 2 sine t, and on the right there's minus 5a sine t. So these need to be the same. But also on the left is plus 0 cos t. And on the right-hand side, it's minus 3a cos t. So 0 and minus 3a must also be the same. And we can't solve this. This linear system is inconsistent. It's not possible to find a constant a which satisfies both of these equations. So our first guess has been a failure. Let's guess again. What went wrong last time? Last time, when we differentiated sine, we also started getting cos terms, and then we didn't have anything to cancel the cos terms out. So this time, we're going to start with both sine and cos. My second ansatz is going to be a sine t plus b cos t. And then we do the same method. Differentiate 2 times, substitute into the differential equation, and then compare both sides. On the left is 2 sine. On the right is minus 5a plus 3b sine. On the left is 0 cos. And on the right side, minus 3a minus 5b cos. So we need to have minus 5a plus 3b is equal to 2, minus 3a minus 5b is equal to 0. And this linear system is consistent. It's possible to solve this. I'll leave it for you to check that the solution is a equal to minus 5 over 17 and b equal to 3 over 17. So now we have our particular solution. I'll just put it on the slide. The particular solution is minus 5 over 17 sine t plus 3 over 17 cos t. When you do this method, when any time you see sine and cos, remember that sine and cos are friends. They always go together. If we see either sine or cos in GT, then our ansatz needs to always contain both sine and cos. Likewise, sine and cos are also friends. Sine and cos always go together. If you see either sine or cos, then you need to have both of them. Another example. Find a particular solution to y double prime minus 3y prime minus 4y is equal to minus 8 e to the power t cos 2t. Here's our function gt. It's a number multiplied by e to the power t multiplied by cos 2t. So this is what we're going to make it in our guess. This is our ansatz. We're going to guess that we have a number, e to the power t, cos 2t. But remember, I said sine and cos always go together. Anytime we have cos, we also need to have sine. So we're also going to have a number, e to the power t, sine 2t term. Always our guess should look like gt, And if we have either sine or cos, we must also have the other one as well. We'll differentiate this 2 times. I'll leave the details here for you to check. I don't want to spend time on this. And then we substitute this into the differential equation, like this. I'm going to try to use colors to indicate this. Gather all of the cos terms together, gather all of the sine terms together. For the cos, we have minus 8 on the left, minus 10a minus 2b on the right. For the sine terms, 2a minus 10 on the right and 0 on the left. So we need a and b to satisfy this linear system. You know how to solve linear systems like this from linear algebra, so I'll just tell you the solution. The solution is a is 10 over 13 and b is 2 over 13. And then we're finished. As soon as we know a and b, we can write down our particular solution. 10 over 13 e to the power t cos 2t plus 2 over 13 e to the power t sine 2t. Now it's time for a theorem. Let's suppose we have 2 differential equations. A y double prime plus by prime plus cy is equal to g1, and using the same numbers a, b, and c, suppose we also have a y double prime plus by prime plus cy is equal to g2t. We have the same left side but different functions on the right. And let's suppose we know a particular solution to each of these equations. Let's suppose we know that y1 is a solution to the first equation, and we know that y2 is a solution to the second equation. Then the theorem tells us that we can add these together. y1 plus y2 solves. Same left side, a y double prime plus by prime plus cy, that's the same because it's a linear equation. And on the right side, we just add them together, g1 plus g2. That's useful if we have something like this. Find a particular solution to y double prime minus 3y prime minus 4y is equal to 3 e to the power 2t plus 2 sine t minus 8 e to the power t cos 2t. We've done the work already because we can split this problem up into 3 easier problems. Instead of doing this all together, we can look at the 3 functions on the right side separately. We know particular solutions to these 3 differential equations. We're just going to add them together. Therefore, this long function in brackets, the green function plus the orange function plus the blue function, is a particular solution to equation 7. Now, there's one issue that we need to talk about before we can finish today's lesson. What we've been doing is we've been looking at the function gt, and we're choosing a similar function for capital Y. But sometimes this doesn't work. There's one thing you need to look out for, which I'm going to show in the next example, and I'm going to show you how to deal with a problem which might occur. Find a particular solution to y double prime plus 4y is equal to 3 cos 2t. Using the ideas that we've been doing before, we look at the function on the right, 3 cos 2t, and we make a guess. That's number cos 2t, so the way I've taught you so far is to guess number cos 2t, and anytime you have cos, you must also have sine. So we guess we also have number sine. Now, I've said we have a problem, sometimes it doesn't work, and I'm saying this is first guess. So this is a clue straight away that something's going to go wrong here. Let's try it. As we've been doing before, differentiate 2 times, put into the differential equation, and simplify. We get 3 cos 2t on the left and 0 on the right. And remember, this needs to be true for all time t. This is a failure. This hasn't worked. It's not possible to choose A and B such that 3 cos 2t is equal to 0 for all time t. Something's gone wrong here. Why did this happen? Why didn't our usual method work? To try to understand this, let's solve the homogeneous equation. Y double prime plus 4y is equal to 0. We start with the characteristic equation, and from the characteristic equation, we find that the roots are plus or minus 2i. So the general solution to the homogeneous equation must be c1 cos 2t plus c2 sin 2t. Because cos 2t and sin 2t appear in the general solution to the homogeneous equation, we can't use the same functions in a particular solution. If we try to do that, then we get what happened before. We just get equal to 0. And then we failed. So instead, we need new functions. And the hint I'm going to give you is, if in doubt, multiply by t. We need 2 functions, which, when we differentiate them, give us cos 2t and sin 2t terms. We're going to try the function t cos 2t and t sin 2t. Anytime we have a problem like this, we multiply by t and try again. Now, note that if we differentiate t cos 2t, we get a cos 2t term and an extra term. If we differentiate t sin 2t, we get a sin 2t term and an extra term. And we're going to hope that these extra terms cancel out, and we're left with cos 2t terms and sin 2t terms. So, let's do our second guess. The second guess is we're going to guess that capital Y is a t cos 2t plus bt sin 2t. That's the first guess multiplied by t. We differentiate 2 times. I'll leave this for you to check. And we substitute them into the differential equation. And we find that, yes, all of the t cos 2t terms and all of the t sin 2t terms will cancel out. And we just have a cos 2t term and a sin 2t term. Now we can do this. Now we can choose our A and our B. On the left, we have 3 cos. On the right, 4b cos. These must be the same. On the right-hand side is minus 4a sine. On the left is 0 sine. So A must be 0, and B must be 3/4. And then we can write down the particular solution. Therefore, a particular solution to this equation is 3/4 t sine 2t. So to recap, if functions solve the homogeneous equation corresponding to a non-homogeneous equation, you can't use the same functions in your particular solution, in your ansatz. Instead, multiply by t and try again. In a rare solution, it might still not work. You might need to multiply by another factor of t and then get it to work. And that is the end of today's lesson. Next time, we're going to finish chapter 3. I will solve some initial value problems. That will be partly revision and partly showing you how we solve a whole problem. We'll look at the method of variation of parameters. That's another way to find a particular solution. And then finally, we will generalize our ideas to higher order linear differential equations. Are there any questions?